All right. I hope everyone's doing well. Let me get the setup all going. Okay. Happy Friday, everyone. Hope everyone's doing well. We're gonna start some complex analysis. Um, yeah, we did a little bit of work on Wednesday. We were talking about the different ways of viewing complex functions. So mainly today we'll be defining essentially what does it mean for a function to be holomorphic from C to C, so from complex numbers to complex numbers. So first of all, yeah, let's just define what we're doing. So this will be lesson 24, intro to, I'll say a formal intro because we did a little bit of like an informal intro to complex analysis. Okay. Yeah, so of course complex analysis arises because we want to include a new number that's a root to a polynomial that before it didn't have a root, right? So of course we know when we square any real number we get a positive number, right? So x squared is always greater than 0 or greater than or equal for any real number. Right? So the problem arises when we want to find roots of polynomials for, say, quadratics like x squared when the number is negative, right? So essentially the main, I guess maybe it's not the main study, but maybe the main motivation, right, is first trying to solve the equation x squared equals -1, right? So it has no solution. At least over R. Singular moduli, yes, I made it to the beginning of one of your streams. Yeah, welcome. So yeah, this is really the start, I guess you would say. Obviously we're getting once you get more into it, you figure out we're not just adding this root of -1, but we also want to ask about, how do we generalize calculus for derivatives making sense in this new space. So initially, I guess you could think of the main motivation is we want to solve this equation, or at least, because it has no solutions, we want to be able to add a new solution. Right, so what do I want to say first, I guess? So yeah, we to be able to solve this, we want to include all of our normal number system, but we want to basically extend it to a larger number system that includes a root of this -1. So we essentially, so we've done some linear algebra so far. I guess I can relate it to that, which is we're essentially creating an extra dimension to the space. So we have the real numbers, and then now we're going to be extending the vector space over the real numbers to include this extra root of I. So essentially we want to be able to write all of the numbers in this new system as, so we want a new system, some new number system, which includes, so it includes all of the real numbers, right? So it includes all numbers like x, but also any multiple of this new number that we're adding I, which is a root of this equation. So any x plus iy where x and y are real numbers. Okay, so you can think of it as a two-dimensional vector space. We're essentially just adding a new basis element, which you can think of as it's the one of the roots of this equation. It's either I or -I, but of course, we just pick I out of like convention. What is the square into a negative? So unique and unnatural. Yeah. Well, for any normal number, right? So yeah, this isn't. I mean, these aren't normal numbers, right? They're not obeying the same relations that the original real numbers had. In particular, once we add this new dimension to the numbers, they're no longer ordered, or at least there's no ordering that respects the multiplication, the field product, right? Welcome, Zach. So yeah, we can. So of course, when you extend these number systems, they add certain things that you want, but then you kind of lose some things sometimes. So what we're losing here is we add a root to this -1, but we end up losing the ordered field. The ordered the orderedness of the field that respects the field product. Or yeah, I'm probably not saying this correctly, but essentially, there's no good ordering on the complex numbers such that, I forget what is the relation with the product. Trying to think. Yeah, I think like you want the ordering to, if two things are, what is it, like if A is bigger than B. I'm trying to think, what is the relationship between the product and the ordering? I think it should be something like if A is bigger than B. Yeah, like if A is bigger than B, then like A times some C should be bigger than B times C, I think. Something like that. Maybe. Or like the sizes of these. Yeah, I don't know. I didn't think about this too much, but there's some. I know there's something to do with the fact that the ordering. I mean, obviously you can put an ordering on the complex numbers, but it won't be like a natural ordering. Like it won't respect some sort of multiplication. I'm forgetting exactly what the it's not that it's a post set. So the real numbers are ordered, but they're also an ordered field, right? I'm trying to remember what the ordering has to do with the field product, though. I'm like blanking on it for some reason. But yeah, there's some sort of relationship between the ordering and the field product that you want, the ordering to respect the product in some sense. And so you can put an ordering on the complex numbers, but it won't respect the field operation. So there's essentially no like good ordering, because if you want an ordering that respects this product, or else the ordering is sort of like arbitrary. Right. Okay. So let's well, first of all, let's say how we multiplied two of these things. So if I take two of these elements, x and y are real numbers, and I take an x plus iy, I take some other x plus iy, maybe I call it a plus b or something, a plus ib. So luckily we can sort of pretend like I is just a regular number, even though it's not a real number, and we can pretend like it has the normal operations, and in the sense that you'll see in a second. So if I want to multiply two of these things together, hopefully this eraser is not too wet. Might need some paper towel if it is. Right. So yeah, we have all these. Let's call it z1, I guess, is some x plus iy, and let's say we have another one, or maybe I'll call it x1, y1, and z2 is some other complex number. So all of these are real numbers. Or sorry, real numbers. Oops. Make sure this eraser is working properly. Something's happening. Yeah, it's just wet. Hold on. I need a paper towel. Give me 3 seconds. Okay, sorry about that. Just wasn't erasing, or it wasn't writing properly. Can they be vectors? What if they're not real numbers? If they're not real numbers, I mean, I is just a symbol, right? So this is really just, you're creating like a two-dimensional vector space over something, right? So really x1 and y1 could be any field. But then it's not really clear like what it means to multiply these two things together, right? So we still need that I squared is -1, or else. Yeah, so initially I is just some symbol. It represents like a new dimension in this real vector space, but there's the extra property that we can actually multiply these two objects together. So that's an important thing. So, wow, this is just not working anymore. I have other markers. Hold on. Right, so what does it mean to multiply these two things together? So we have z1 times z2. Right, so x1 plus I y1 times x2 plus I y2. Right? And then we can just pretend that these are regular numbers. The only thing we have to remember is that when we multiply two i's together, we get a -1. So that's the only difference. So this is x1 times x1, times x2, plus x1 y2 times I plus x2 times y1 times I, plus, now it's I times I, which is -1, times y1 times y2. Okay. So if we combine everything together, then this is just x1, x2 plus I times x1, y2 plus x2, y1. So yeah, let me put everything in the front. So this is, so it doesn't keep doing that. Oh, yeah. So this is x1, x2 minus y1, y2, plus I times this stuff. Hello, Kyler. Sorry for. Oh, thank you, man. Nah, yeah, I appreciate it. Yeah, it's not. It's been tough, but I'm working through it. Yeah. Right. So two complex numbers, they're of this type, and then yeah, all we need is that the I times I is -1, and then you can kind of see that now these are roped back into the real part, so we can pull these back to the front here, and this is just x1, x2 minus y1, y2 plus I times this sum. So yeah, this is called rectangular coordinates. So later, I'm not going to go too much into this now. We haven't really gotten into enough of the material to really explain this, but there's also a polar coordinate form. Actually, there's really three forms. So there's a way we can say this is we can just call this z, or we can say that this is in polar form. It has some radius and some angle argument. So we can call this, sometimes they call this the modulus, and sometimes they call this the argument. But we were talking about this on Wednesday. This is just like mathematician speak for, you know, we wanted to create a new name for something that already has a name, right? Like this is the size of the number, and this is just the angle of the number. I guess you could call it the argument, the angle it makes with the positive x-axis. Or you could just think of it as like the polar coordinates of the, you know, you can forget about complex numbers altogether and just think this is like rectangular coordinates of a point, you know, on the Cartesian plane, and this is the polar coordinates of that same point. So is the modulus the norm? Yeah, exactly. That's another name. Yeah. So the modulus is just the norm of the number, or the, you know, the size of the number, or the metric of the number. You know, all of these things are sort of equivalent synonyms. But in complex analysis, they liked, especially this book, this, yeah, if you didn't see the book already, this is the Green book. So this is what, Robert Greene and Stephen Krantz. Right, so in that book, they refer to the size of the number as the modulus and the angle as the argument. And of course, the modulus R is just the Euclidean norm. So again, you just view this point as a normal point in the Euclidean plane. Then this is just x1 squared plus y1 squared. Or, yeah, r squared is. Okay, and then the argument is a little bit more complicated, which we can get into at a later point. But I just want to point out that a lot of the words in complex analysis, they kind of create these new words for things that we already know what they are. Like this is just the Euclidean norm of the number, right? This is just the norm. Yeah. Complex analysis done hard. Yeah, I mean, it's always harder for students if they don't understand what the words mean, right? So I always feel like it's a little bit confusing. Like, why go through the process of teaching students about Euclidean norm if then we give them the norm, but now it's complex analysis, so now we call it something different. So I mean, I don't know. Doesn't seem to make a lot of sense to me, but I don't make the rules, so. So yeah, we have two numbers, we can multiply them. There's actually a nice way to multiply them, which we were going over on Wednesday, if they're already written in polar form. In which case the sizes of the numbers just multiply and the angles actually add. So we'll get into that eventually. I don't want to write out that theorem, but we're going to start out a little bit in the basic part of the book. So we're first going to define what does it mean for a function to be holomorphic. Actually, first we're just going to define what is a function between two complex numbers. And are there any questions before we start? So really all we've done so far is just said that, you know, there's this number system. It's made up of these real numbers, but we have this two-dimensional real space where now I've added this new element I. So every element is some x plus iy, real number xy. Also, something that's important, which I'll just keep up on the board at the top here for us, is the z bar, which is the complex conjugate. So this is x minus iy. People upstairs watching soccer. Right, so we have z and z bar, and for any function between complex numbers and complex numbers, we can also view it as a function of z and z bar, and where we can view the output in this z and z bar coordinates. So, and it turns out that this is actually an advantageous way to look at functions. So functions from complex numbers, or maybe I'll just say functions f. Complex numbers to complex numbers are equivalent to, so because this is a two-dimensional number system, essentially you're just, it's like a map from R2 to R2, which just means that essentially it's just like two functions on two variables. So it's basically equivalent to two functions which are u of xy, and we usually call it the next one v of xy. So really C, you can think of C, I mean, essentially as a set. It's equivalent to R2, right? It's just a two-dimensional plane. You have, one basis element that's like orthogonal to 1, which is I. And so if you ignore the algebra structure and you just look at the vector space structure, it's essentially just R2. Which means that functions from R2 to R2, this is just two functions of two variables. So you have u of xy and you have v of xy. Right. Any questions here? No, it's French. Have you heard of the block sphere? Maybe? Block sphere? I don't know. It sounds a little bit familiar. You could remind me. The W plane. No questions so far. Okay. Right. So, right. So actually, there's a way to translate any function from C to C. You could write it in rectangular coordinates, and you could think of this as like the rectangular output. Like this is the x coordinate of the output, and this is the y coordinate of the output. And you can think of the output as like u of xy plus I v of xy. But there's another way to look at functions where, and I always found this very confusing when I first learned it, but you can actually view the functions as functions of these two sort of transformed variables. So instead of viewing things in the xy variables, we can view them as z and z bar. And this lets us write certain functions, for example, like I can create like a polynomial in z and z bar, for example. So we could have something like f of z bar and I just made up one which was like z squared z bar plus z bar squared. Okay, so this is one way of writing the function, but this is, I just want to make it clear that you can write a function this way, but there's an equivalent way of writing it in terms of u and v and x and y. Right. So I didn't do this out on this paper, but I think maybe it is useful, I'm thinking now, to try to convert this function into the other form. Just to make it clear that you can sort of go back and forth, right? So, yeah, any questions about this? So here it's interesting because we're actually using the product to define the function, and this is only possible because we can actually multiply these two things together because we've defined what it means to multiply complex numbers, right? Well, maybe I didn't like explicitly prove that it all makes sense, but we at least showed how to do it for, z1 and z2, two arbitrary complex numbers. Well, I guess that does define it, yeah. Right, so yeah, let's just go real quick through this example. Let's try to convert this into u and v, and yeah, hopefully I don't mess this up. The water off. The block sphere is used to represent a qubit in quantum mechanics, nothing to do with Riemann. Oh, okay. Yeah, so that's like a projective sphere or something, right? Like you're modding out by the scalar multiplication. It makes sense since real of z is equal to 1/2. Yeah, exactly. That's what we're gonna write in a second. Yeah, exactly. Thank you. So yeah, let's try to convert this. So yeah, we can in the chat, Mavert says we can write the real part of z which is the same thing as x, right? This is our x plus iy. This is the x part. And this is just 1/2 z plus z bar. And similarly, the imaginary part of z, this is just the y. And this is 1/2 of, I believe it's z minus z bar, right? Or do we need to multiply by something? I, right? Yeah. Or is it negative I? What is it? Is it just 1/2 z minus z bar, or do we need an I somewhere? Oh, it's just z minus z bar. Okay, the x's cancel. Okay, yeah, no, this is good. I feel like there should be an I somewhere, or am I could be mistaken. I should have to divide by I, so I'm thinking it's negative I. Is that it? So Maver has one. Yeah, okay. Must be in the denominator. Yeah, so dividing by I should be the same thing as multiplying by negative I. So I think this is right. Right. So then, did I make this problem too hard? Is this should be easy, right? I confused myself. I can't tell how easy this is. How do we convert this to, okay, so we want to be able to write it as like u of, so we want to be able to write it as u of xy plus I of v of xy, right? That's what we want to do. Right. I feel like this is not that hard, but I confused myself somehow. Let's see. Any help from the chat? Z minus z bar over 2I. Yeah, that's what we have here. So that's the imaginary part. That looks correct, right? Okay, so basically, yeah, we want to be able to convert these z's and z bars to x's and y's. Oh, okay, yeah. So then we should be good. Yeah, okay, this is not that hard. So f of xy should be, yeah, okay, we're good. So it's x plus iy squared times x minus iy plus x plus iy times x minus iy squared. So this is multiplication at the end. So yeah, okay, yeah. Got it at the last second. Right, so basically we're just going to substitute z and z bar with, you know, their equivalents, right? So z is x plus iy, z bar is x minus iy. And now what we want to do is we want to rearrange everything so that we have it as like some real part plus I times something else. And the first part is going to be the function of u, and the second part is going to be the function of v. So let me just swing back around up here for a second. I'm just going to expand this a little bit, so let me FOIL these out. So this is xy plus 2I, x squared plus 2I xy minus y squared. So all this times x minus iy, and then plus x plus iy times x minus iy squared, so that is x squared minus 2I xy plus y squared, or minus y squared. Okay, Okay, I'm doing this very messily, but this is what we have so far. So yeah, and basically I just want to continue distributing this and then rearrange everything with the everything with an eye on the right and everything without an eye on the left, and that's essentially it. Take the XX bar out. ZZ, whoa. I'm not sure what you mean, Rex. So yeah, I'm just gonna continue. I know I'm going like backwards up the board. It feels weird, but. Okay, so basically I'm just gonna continue foiling this out. So x times this. So x cubed plus 2i x squared y minus y squared x minus iy x squared plus 2xy squared plus iy cubed. Okay. Plus, okay, yeah, this is a little bit more than I thought it was going to be, but okay. X cubed. And if I make a mistake here, somebody let me know. You'll have z plus z bar left in the brackets. Z bar will create a real number. Oh, I see what you're saying. Okay, yeah, that might work too, but let's just finish. I already did it out, but yeah, I think you might be right, Rex. Okay, so yeah, minus 2i x squared y minus x y squared plus iy x squared plus 2xy squared minus iy cubed. Okay. So some stuff cancels. What cancels? This cancels. So we get 2x cubed. Let me just get all the real part in the front. So there's 2x cubes. There's a 2 minus y squared's x. So minus x y squared, 2 of them. What else? Okay, so plus 2xy squared. Oh, wait. Wait, what? Oh, there's 4 of them. So there's minus 2 of them, plus 4 of them. So there's actually just plus 2 of them. And then it's plus I times 2x squared y. I know those cancel. Oh, wait, all the y's cancel? No way. Wait, what? Is that right? Wait, there's no imaginary part at all? Huh. Okay, this goes back to what Rex was saying, I think. Z plus Z bar left in the brackets. Huh. So, I don't know, maybe somebody can check this on Wolfram or something. Is there really no imaginary part? So this is just a real function then? Does that make sense? Huh. Weird. Okay, well, I mean, then, yeah, if this is correct, then this is U, and then V is just the zero function, I guess. Something seems off, but it could be right. Okay. All right. Yeah, that's right. I thought maybe I did something wrong, but okay, can we look at the function and see why it's real? So you have z squared, but that doesn't have to be real. So yeah, Rex was saying something about we had z bar, so we know that's real because that's the modulus squared, right? Z bar, this is the size of z squared. So that's a real number. But then we have this extra z here. Oh, okay, so it's so you can factor out the modulus and then you get z plus z bar, which is real. Okay, I see. That's what Rex was saying. Okay, I see. Okay, that's fine. Right. So then u of x here is just 2x cubed plus 2xy squared, and then v of xy is just 0. Interesting. All right. So yeah, that was just an example of how we can write a function as a function of z and z bar. And it can be, some complex output, like we could multiply z and z bar together, or some polynomial in z and z bar. That will be a function with complex output. But if we translate what z and z bar mean in terms of x and y, the rectangular coordinates, now we can write things in terms of the u and v functions that we were saying. So there's always a way to translate back and forth, basically, is what I'm trying to say. And in this case, the u we got was this real function here, and the v we got was this 0 function, which is also real. I had to scroll up while I'm a genius. Scroll up for what? Singular? Okay, so we can write these functions in terms of z and z bar, and now we're going to go to a definition. So we're going to say that a function from c to c, if it's defined on some open set, and it's, maybe I should go a little bit into what these partial derivatives mean, but actually no, it's just the normal partial derivative, right? Or maybe I could do some examples first, but okay, yeah, so let me go back to that example I was just looking at, and let me just point out that if the functions are differentiable, there's a notion of taking a partial derivative of f with respect to this z variable, which, again, when I first learned this was a little bit confusing because, I didn't see z as like a variable that I could differentiate. It seemed like it was two variables to me, right? Because z is, x plus iy. But you have to think of it differently. You have to think of it as like a change of coordinates between a two-dimensional space to another two-dimensional space. So z is actually just one variable of this transformation, but we also have z bar. And without z bar, like z is not a basis for the complex numbers. You need both z and z bar, right? It's not a, complex numbers are two-dimensional, right? So we need two basis vectors. So, but yeah, I guess maybe I don't want to go too much into like the theory of it, but you can sort of just pretend that, at least when you write the function in this form, you can just pretend that these are like normal variables. So like when you're taking a derivative with respect to z, you're just pretending that z bar is constant, and you're just taking the derivative using whatever power rules that already work for the real numbers. So I'm like cheating a little bit here because I'm not really explaining why this works, but that would take a little bit too much time. So let's just go through the process of actually taking this partial derivative, and you'll see that it works, essentially the way that you would think that it would work from single variable calculus. Differentiable implies continuous. Yes. Yeah. So yeah, that's true for real variables, but it's actually stronger for complex. So if a function is complex differentiable, it's not just continuous. It turns out if it's complex differentiable on some open set, it's actually infinitely differentiable. So not only is the derivative continuous, but the derivative of the derivative is also continuous, and etc. But yeah, let's just take this derivative. So let's just take the example function again, take the partial derivative with respect to z, and you'll see that it essentially works like we're pretending like z is just some normal variable. Right, so here we can use the power rule. We're pretending z bar is a constant, right? So this is just 2z bar, because power rule for z squared says we pull down the 2z, and then z bar is a constant, plus, and then z derivative is 1, so this is just z bar squared. Okay, and then we can take the derivative with respect to z bar as well. And it works again the same way. We're just going to pretend that z bar is our variable and z is a constant. So the first thing is just z squared times 1, since the derivative of z bar is 1. And then z bar squared, so z bar squared has derivative 2z bar, and then z is a constant. Okay. So for complex analysis, it's going to be very important whether or not this derivative vanishes or not. The derivative with respect to z bar. You can think of this as like the antiderivative. So it's going to be very important that the antiderivative is equal to 0, essentially, for complex analysis. So if this whole thing is equal to 0 on some open set is like, you want to think of like some open ball, but it could be not perfectly shaped, but essentially an open set is just some set where if I pick any point, there's always some open set I can draw around that point where I'm still contained in the set. So we'll call this, usually we'll call this open set U. So the definition is that a function from C to C, so f from C to C, which we could write in terms of z and z bar, like in terms of like for this example. A function from C to C is holomorphic on some open set U, or yeah, I mean actually technically it would be from U to C. So a function defined on some open set to C, where U is some open set in C. We say it's holomorphic if this partial derivative vanishes for every point in U. So that's a very important definition in complex analysis. In particular, this function is not holomorphic because this never vanishes on any open set. Yeah, I don't think it vanishes. Maybe it vanishes. It vanishes at 0, right? But that's not an open set. That's just a single point. We need it to be 0 on the entire open set U. Okay, so let me, first, is there any questions about this? I'm not being like super formal about what this means, but I'm allowing you to use your intuition from multivariable calculus, like from 2-variable calculus, just pretend our 2 variables are z and z bar, and then you would just take the derivatives the normal way. Yeah, I'm going to write the definition of holomorphic in a second. It's not really the definition that's too interesting, though. So there's many different definitions of complex differentiable, and they're all equivalent. So any one particular definition is not really that important. We'll write it in a second, but I want to point out that there's, if we assume this definition, we can actually show that it satisfies all the other definitions as well. Yeah, so we have analytic, like it's equal to its Taylor series. We have the original definition, like complex differentiable, like in 1-variable calculus, where we just take a limit as h goes to 0, f of a plus h minus f of a over h. But our definition of holomorphic, which we're about to write, is separate. But as long as it's holomorphic on some open set, then all of these things are basically equivalent. So that's like the magic of complex analysis. So essentially a function from some open set to C, we're going to call holomorphic if this partial derivative with respect to z bar vanishes on every point in U. So that's the definition, which I'll write right now. Okay, we got about 15 minutes more. Okay, so in the green book, the function theory of one complex variable, this is 1.4 section, definition 1.4.1. So it says a continuously differentiable function on U to C, so some open set U, is holomorphic if the partial derivative of f with respect to z bar is 0 for all points in U. So for any point in U, P, I look at the derivative at that point with respect to z bar, and it's 0 for every point. It has to be true for every point in U. It can't just be for like the center of the circle or something like that. Just as a short explanation why the function is real, I think we got it, yeah. So it's the modulus squared times z plus z bar, and z plus z bar is 2 times the real part. Yeah, so it's a product of two real numbers. Yeah, exactly. Yeah, thank you. Right, so what does continuously differentiable mean? It just means that, so all the partial derivatives, if we view this as a real function from, some subset of R2 to R2, then it just means that all the partial derivatives of both these functions, remember this is just two functions of two variables, and both of those functions, the partial derivatives are continuous. So not only do they exist for all points, but if we look at the function which is the partial derivative of both variables for both functions, then they're all continuous. So if that's true for all the points in U, and the partial derivative of f with respect to z bar is 0 for all those points, then we just call it holomorphic. So this is just a definition. But like I was saying, you can show that if this is true, if the function is holomorphic, then it will also be analytic, which we'll probably show eventually, but not today. And also, if it's holomorphic, then it's analytic, and then it's also complex differentiable. So you'll see a lot of these synonyms used interchangeably in different textbooks. Some textbooks will start with one definition and try to prove the other one, or they'll start with the other one and try to prove the first one. So it really just depends on what source you're looking at. But you do need to stress, though, again, that this is in an open set. If it's just true at like one point, like a closed set, for instance, which is just a single point, it doesn't necessarily need to be analytic anymore. So we wouldn't call it holomorphic if the derivative with respect to z bar was 0 just at a single point. Hydrate, yeah, I had a water. Where did the water go? I think I left it upstairs. Yeah, actually, let me maybe take a break to get the water in a second. So, okay, yeah, we'll jump into the Cauchy-Riemann equations in a second. But let me just go grab a water because I actually do need some water. Okay, I'm back. Got my water. So yeah, we're gonna do the Cauchy-Riemann equations in a second. So Cauchy-Riemann equations basically take this definition. They say if it's holomorphic, what does that mean about the rectangular partial derivatives? So once we instead, if we think about the function as just, two real functions of two variables x and y, what does this relationship say about the partial derivatives in the rectangular coordinates? Okay, so yeah, this is our definition for holomorphic. Any questions about this definition? Okay, no questions. Okay, so the next lemma, this is lemma 1.4.2. And this says if a function is holomorphic, f from u to c is holomorphic. Then what does it mean about the partial derivative? So it means that the partial derivative of u with respect to x is actually equal to the partial derivative of v, the second function, with respect to y, and that the derivative of u with respect to y is the negative of the other one, of v with respect to x. So you get this weird relationship where the x derivative of the first variable has to be equal to the y derivative of the second variable, and the other ones are sort of equal up to a negative sign. But why does it work for z bar and not z? What do you mean? The definition for holomorphic? So there is a definition for anti-holomorphic, which is that the derivative of f with respect to z is 0. And you can sort of just think of an anti-holomorphic function as being like holomorphic in z bar. So there is sort of like a symmetry here where you can define holomorphic, you can define anti-holomorphic, and they sort of have similar properties. It's just that holomorphic functions include like a symmetry first. But other than that, they behave very similarly as holomorphic functions. They just flip the orientation. I don't know if that answers your question. Does that answer the question? Okay, so this is essentially the Cauchy-Riemann equations. This is just some relationship between the partial derivatives of the two real functions making up the function to c. No, you're good. You're good. No, I mean, it's a good question. So, like, why do we say that? Why does df dz have to be 0, right? Why not, or z bar, right? Why not df dz, right? And you can require df dz to be 0 in some open set, and that's just called an anti-holomorphic function. But essentially, they behave very similarly to holomorphic functions. So the study of them would be very similar, is essentially what I'm saying. What is the proof of this? Proof is pretty simple, straightforward. So we can write df dz bar. If you track what's going on here with this change of variables, this is very similar to when we were changing from z and z bar into x and y. Df dz bar, this is just 1/2 du dx minus dv dy plus I/2 times dv dx, or sorry, dv dx plus du dy. So when we write it in this form, it's very obvious that for this to be 0, these two have to be 0. Sorry, this needs to be equal to this so that this cancels. This is 0. And this needs to be equal to the negative of this so that when we add them, it's also 0. For this to be exactly 0, the real part needs to be 0 and the imaginary part needs to be 0. And that's exactly equivalent to the Cauchy-Riemann equations that these derivatives are equal and that these derivatives are, oh, sorry, I forgot a negative I. Oh, no, that's right. The definition seems backwards. Z should be holomorphic, Z bar anti-holomorphic. Oh, well, no time. No. So it's holomorphic if the derivative with respect to Z bar is 0. So we're basically saying all of the derivative is in the Z part. So that's holomorphic. If the derivative with respect to Z is 0, then that would be anti-holomorphic because all of the derivative part is in the Z bar part in that case. So you have like a holomorphic function, but it's holomorphic in Z bar, which means it's holomorphic in a reflection, which means it doesn't preserve the orientation. Yeah. Yeah, so this is Cauchy-Riemann equations. The proof is super, super simple. It's literally just you write out what the derivative is in rectangular coordinates in terms of the derivatives of x and y. And then for this to be 0, which is just by definition, that's what holomorphic means, right? It's holomorphic if this is 0, and this is 0 if and only if the real part is 0 and the imaginary part is 0. So if and only if this is true, and if and only if this is true. Or if and only if this is true and this is true. Then this derivative is 0. That's also why it needed to be defined on an environment of U instead of pointwise. Why exactly are you saying? So if the derivative is, yeah, I guess if it's just 0 pointwise. Oh, I see what you're saying. Right. Yeah. Could you say that in other words? I feel like I understand what you're saying, but yeah, I think you have a good insight there. I kind of want to expand on that. So yeah, what would happen if the derivative with respect to f of f with respect to Z bar was 0 just at a single point, but not any points around it? I think for the function yeah, could we write out a function where that's true? Maybe like z squared plus Z bar squared or something? Like this function I think is, the derivative is 0 at 0 of Z bar, but not in any open set, right? So this function's actually not holomorphic, even though the derivative of f with respect to Z bar is 0 at the origin. It's not 0 on any open set around the origin. So what's going to end up happening is there's it won't satisfy this definition of holomorphic, and it also won't be analytic. So there won't be a Taylor series in Z where we can expand this function around 0. Essentially, any polynomial where you have any sort of Z bar in there, it's not going to be holomorphic because the derivative with respect to Z bar is never going to be 0 on an open set. It's only going to be 0 on some discrete set, whatever the roots are of the derivative. Okay, I can keep going, or we could stop here. I'm not sure. Any questions so far? So we've gone through what a complex function is. A couple different ways of writing down these coordinates, either rectangular coordinates, polar coordinates, or this Z and Z bar notation, which is quite useful. And then we said it's holomorphic if the derivative with respect to Z bar was 0 on an open set. And then this lemma now says that this is implies that if it's holomorphic, then we have a relationship between the partial derivatives. And this is the Cauchy-Riemann equations. Okay, yeah, I think this next proposition is probably not super important. Maybe I'll just talk about harmonic for a second, or we could do some problems. But I did a lot of problems on Wednesday, so maybe I'll just define harmonic real quick. Actually, I could probably do this next time. Yeah, I don't feel like going into this just defining it and not saying anything about it. So yeah, we'll talk about harmonic next time, I guess. So it turns out that if a function is holomorphic, then the real part and the imaginary part are both special functions which have nice properties, which we call harmonic. And that's just a property on the second derivative. So a function's harmonic if you take, so like these real parts u with respect to x. So if I take the second derivative and I add it to u with respect to y squared, then this is actually just, if this is 0, then we call it harmonic. So you sum up the two partial derivatives, the second partial derivatives, and if you get 0, this is also called the Laplacian of the function. So if the Laplacian is 0, we call the function harmonic. And it has some nice properties, like we were going over on Wednesday, how it has this mean value property for one of the problems, where the value of the function at any point is sort of like the average of the values of the functions on some circle around that point. So yeah, these harmonic functions have some nice regularity properties about these sort of averages, and it turns out if a function is holomorphic, then the real part, the u part, and the v part are both harmonic. Okay, so thanks for tuning in. This was a quick little hour introducing complex analysis. We'll do a lot more into this, probably at least like 5-10 more lessons. But yeah, we'll get into some very, very fun formulas here. There's like the Cauchy equation, Cauchy formula, where you can define, there's like a nice integral formula for a holomorphic function. And we can also prove some nice theorems like Louisville theorem from Cauchy's formula. So some cool integral formulas coming up, and we'll be able to prove some of these higher, more advanced complex analysis theorems using some of these more basic theorems, which we'll go over next time. But yeah, thank you, Rex. Thank you for everyone else. I appreciate it, Kyler. Who should we raid? Maybe Don is streaming. Let me find out. Thanks, everyone. Let's see. Twitch. Who's streaming?
Word in Portuguese?
So I want to raid high potential, but I think it's something in his settings won't let me for some reason. Let's go with Mr. Lucarino. Right. I don't know too much about the streamer. But yeah, I hope everyone enjoys. And I will send it over to them now.